Hi, everybody. You're not going to want to miss this episode of the Into the Impossible podcast featuring a scientist I've known for well over half my life. Incredibly impressed with him when he was an undergraduate at Brown University, where I was a graduate student. He is a theorist by training, but he works on some of the most cutting-edge aspects of physics, ranging from information theory, quantum mechanics, the multiverse, one of the foremost proponents of visualizations of the multiverse and inflation, but also an old-time cosmologist and a young person's persona, in that he really doesn't just dismiss things because of received wisdom. In his book Cosmological Koans, which is one of the most delightful books I've ever read, in kind of the spirit of a Stephen Hawking or a Carlo Rovelli, you will find yourself betwixt and bemused by this wonderful book, which is really a travelogue that takes place in the 1600s and kind of teleports the reader through time and space to encounter the most magnificent and mesmerizing concepts in the world of physics and cosmology, ranging from the arrow of time to cosmological inflation to the Big Bang, the steady state as well. And ultimately, the meaning of paradoxes called koans. In this case, it's Professor Anthony Aguirre, university professor at the University of California, Santa Cruz, way up north, one of the northern UC schools in this wonderful university that I am a part of. And I'm proud to be a part of this university because of professors like Anthony. So I do want to alert you to this amazing podcast. You're going to love the interview. And we covered so much. He's a close friend and colleague of Carlo Rovelli himself and Max Tegmark and many other great scientists, Sean Carroll, that we've had on the podcast. And I can't believe that someone so skilled in sort of the hardcore quantitative arts of theoretical physics can write such a magnificent book that's kind of part Zen in the art of motorcycle maintenance, combined with a book on modern cosmology. So you're not going to miss it. Please do me the favor of subscribing to this channel on YouTube, or if you're listening on iTunes or Stitcher or Spotify or any of those places, follow it, subscribe to it. If you can, leave a review. That really helps me. We're up to about 200 reviews so far. I can't tell you how much that means to me. That's all I'm asking for. And so for now, sit back, enjoy the phenomenal, the effervescent Anthony Aguirre, a man I've known since he was a young kid, and now he's a university professor, the highest honor we can give to a faculty member at the University of California, and for good reason. So enjoy this episode with Anthony Aguirre, and stay tuned for more wonderful guests coming up on this podcast.
Any sufficiently advanced technology is indistinguishable from magic.
And today it is a great pleasure to talk to a friend of mine, a colleague, a fellow professor in the same university, that being the University of California, and that is Anthony Aguirre, who is a professor of physics at UC Santa Cruz, home of the banana slugs. I always forget.
That's correct.
That's good. Okay. So banana slugs, that's why you never come down to UC Irvine, because there might be an anteater that mistakes a banana slug for an ant and eat. Anyway, I don't know why I would bring that.
It's also very dry. We like our moisture.
That's right. Well, Anthony, I've known you since you were an undergrad at Brown University when I was a graduate student. So much older, so long ago, and yet it won't even come close to talking about the subjects of your book, which take place in the 1700s. And that book is really a work of art, Anthony. We haven't talked very much recently with the pandemic and so forth. I stopped by your neck of the woods about a year and a half ago, right before COVID sort of kicked in, and I wanted to stop in and see you, but we didn't get to connect. But nevertheless, here we are. And in that time, I hadn't read your book at that time, even though it was published by the same publisher who published Losing the Nobel Prize, which is Norton, and endorsed by some of the most luminous luminaries in the world, including my new friend Carlo Rovelli, who is teaming up with me and another Italian physicist to make the first audiobook of Galileo Galilei's a dialogue on the two world systems, which plays a role in Cosmological Koans. And that is really a book, as Carlo said, a gem of a book. I found it magical. I found it really delightful. And, it's like I read these books and they're written, and I'm sure if you ever get a chance to look, you can skip over most of my book because a lot of the physics in it. It's the personal story that's different. This book, you really can't skip over so much. And
very dangerous to do. Yeah,
it is. And it has such a delightfully playful approach to the biggest questions in the universe, the smallest things in the universe, and everything in between. So first, welcome to the Into the Impossible podcast. I've wanted to have you for a long time. I'm so glad you can make it.
Thank you. It's great to be here.
So this book seemingly came out of nowhere, and yet there's nothing really else like it. It's sort of, when you pick it up and you see Koan, you think, I immediately thought, oh, great, Anthony's gone woo. He's gone woo-woo. He's gone to the Woo-Lee master side of things. No offense if whatever his name is, Gary or whatever his name is out there. But I was a little afraid. You see Koans, you see the physics of God and the God equation, which is now coming from our friend Michio Kaku, who will be on the show shortly. What inspired you to write this book, Anthony?
I think it was really thinking about what I find inspirational as a physicist. I think there's a sense that what physicists do is like, sit down and do dry technical stuff, and they try to make predictions, and they run gigantic experiments to test physics theories. And all of that is true. All those are part of the job description. But for most of the people who are really excited about physics, like you and I and many of our colleagues, that's not why we got into physics, to like write grant proposals and sit on committees and like look for funding for massive, experimental programs. We got into it because
I like that. I like being on committees.
You like being committees and fundraising.
Lonely. I get lonely.
Yeah. Gotcha. But I think most of us got into it because we see this world around us and want to understand how it works. And as we discover some of what science has discovered about how it works, we realize how crazy and mysterious the truth of how the universe works really is. That it's not at all the way we think it is, in our everyday life. We've got objects and they kind of move around, and there's physics that describes that. But as we get deeper and deeper into it, we understand, how mathematical it is, how paradoxical it is, how counterintuitive things are, when compared to sort of our everyday understanding of things. And the magic, I think, of physics is seeing that there's this kind of secret world behind the scenes. There's this whole other way of looking at what the world is doing, which is different and also true and mysterious. And you can come to understand more of it, but the mystery remains. And in fact, I think part of what inspired this book was the feeling that the deeper you go, the more you understand about how the universe works, the more mysterious and the more subtle and interesting the questions get. And so my hope for this book was to really try to give a reader a bit of that experience, that there are strange things about the universe, and there are big questions in physics, like what is the dark matter? This is a big, interesting question. But there are a whole bunch of other big, interesting questions that are very subtle and very deep about the nature of reality that you don't read about so much. And so that's one goal. And the other goal, I think, was to give a little bit more of the, I write in the book a wonderful description by Albert Einstein, who said one of the most beautiful experiences that a person can have, I'm paraphrasing here, is of the mysterious. To see that behind, as I was saying, behind the sort of facade of the world, there's this deeper reality that we can only touch upon. And I wanted to try, if I could, to give the reader a little bit of that experience. And as I recount in the book, there's some parallels to this and the process that takes place in Zen Buddhism, where the idea is not to sort of impart knowledge on you, but to give you an experience, to confront you with a question and confront you sort of so forcefully with that question that you have no choice but to sort of be all about that question and in awe of sort of what the different answers could be to that question, or how, or what that question means, what it means for you. So there was an inspiration in this method of Zen of kind of sort of confronting the student over and over again with more and deeper versions of fundamental questions. And that's kind of what I wanted to do in the book, to take the reader and bring them to this place of, here's what we know about reality, but there's this question. Here you go. Have at it. Think about that. And to bring them to that place where that's so wonderful as a physicist to say, I don't get it. I don't understand. How can reality be that way? And yet it's got to be like this, or it's got to be like this, but they're both super weird. That feeling of strangeness of the way that the world really works. I wanted to help the reader come to that.
Yeah, I find that dichotomy that we have as physicists. On the one hand, people, as you say, look at physicists towards the end of the book, you talk about how, in principle it should be. I think Rutherford said something like that. Everything is either physics or stamp collecting, meaning that the laws of chemistry can come from the laws of physics, the laws of biology can come from chemistry, which comes from physics, et cetera, et cetera. So there's this kind of, so we have this, swagger associated with ourselves that we're, kind of the top apex predators of the scientific world. And yet, this book really points out that undermines that pyramidal structure, because you really reveal not that we're ignoramuses, but just that, as Wheeler, John Archibald Wheeler said frequently, and you quote him throughout the book. I'd love to know if you ever met him. I never did, but Wheeler said something to the effect of, as the island of knowledge grows, so does the boundary of our ignorance. The coastline of our ignorance grows too. How do you handle that? When you have young kids, I have kids, they think of us as just like we're Wikipedia, basically. You put in, ask them a question, out will come an answer. And yeah, we can handle most of the ones that are tough for lay people. Why is the sky blue? What caused the galaxies to move away from us? Whatever. But we can't answer, what happened before on the Tuesday before the Big Bang yet. We can't say what are electrons made of yet, or what is the true fundamental theory. Do you think that's just a byproduct, in other words, of our success, in that we've explained so much with so little, just the laws of mathematics and some observations? We've only been doing this since about the time of Galileo in a quantitative form. But what do you attribute that to? And are you uncomfortable, like, not knowing? Because it seems like a koan, if I'm not mistaken, is sort of a paradox that makes you uncomfortable, or should.
Yeah, I would say, my reaction to that is sort of one of delight and opportunity, in that I think once you really understand something really well, it's not that interesting to keep thinking about, right? Certainly as a physicist, we learn Newtonian mechanics, for example, in high school or college, and you can go sort of deeper and deeper into Newtonian mechanics, but nobody wants to just spend 30 years doing inclined plane problems. Like, you can get really good at them, but okay, where's the challenge? It just it's not interesting anymore. So I think what is amazing about the way the universe has turned out to be is that it is both comprehensible, that we can make tremendous progress in understanding how it works, to the extent that we can, make predictions that show 11 decimal places of accuracy. We can launch satellites along the right trajectory to basically then just coast their way to another planet. That we can do all these things with enormous precision, and yet it also holds enough mystery that there are so many still open, unanswered questions, and even some of the most basic, simple ones, like you said, what is an electron? We know everything about how electrons act in the sense of predicting everyday phenomena that involve electrons. We can do it so well, we can devise devices and with whatever characteristics we want, whatever behavior we want. We can build computers with gigantic amounts of computation built into them. But the question of what is an electron exactly, in a way that is really sensible and really feels comfortable in a sense, and you feel like, yes, you told me, now I really know what an electron is. That doesn't exist at the moment. And that's an amazing thing, to be able to understand the world so well in certain ways, but still have that mystery there. But I'm so happy that that's the case. I would find it so disappointing if I felt like the whole world was just fully understood. We understood how everything worked, and there was no more mystery there. I would find that terribly disappointing. Other people might find that comforting and pleasing, but not me, though. So that's my own personal preferences, I guess, that I would want that mystery to remain there.
Yeah, and it sort of echoes a conversation that I had with the late great Freeman Dyson, and it actually did involve religion. I'm forbidden to convert by nature of what my religion is. He was a member of the Jason Society, allegedly. It's top secret. But they meet here in San Diego, California, and La Jolla. And so he'd come to visit in the winters. For some reason, he didn't like being in Princeton in the middle of January. So he'd come down here and they'd spend some time. We got to know each other really well. And he's actually like 90 years older exactly than one of my kids. And they got along really well. And we talk a lot. And sometimes we talk about religion, because he was famous for kind of being an agnostic, in some sense, devout agnostic, as I call myself, is not too far from what I perceived him to be. And I said, well, what is it about religion, that is interesting to you? And why don't you, as most, scientists are fairly strongly held in terms of secular? And he said, well, God is a mystery, and science is a mystery. There may be puzzles along the way, and the distinction he made is, puzzles can be solved. The mysteries perhaps can't be. You were always a better student than I was, Anthony. So you could solve some homework problems or whatever that I could never do. And but there might be mysteries that you can't solve, and I can't. Nobody can solve, and that's kind of the essence of these koans. So talk us through what inspired you. I mean, are you a Buddhist? I mean, have I known you for 30 years and secretly you're a Buddhist?
I've dabbled in the sense that I've certainly read Buddhism. I've sat Buddhist meditation retreats. So I don't like being any ist too much. I still, I do consider myself a scientist, but that's a bit necessary. But I try not to adhere myself too strongly to any particular set of beliefs, other than the ones that I've feel a really good. Have sort of a professional interest in some sense. But so yeah, certainly I've read Buddhist philosophy and done some practice. But I think this is the purpose of this book is not so much about trying to merge physics and Buddhism or something. I think there are some nice parallels in certain places, but it's more here is this parallel in method, really, and a little bit in experience, like the sort of mystery and awe and kind of don't know, like, God, I just don't know, that is part of some of the most fun, interesting science. I think has a parallel in the questions that Buddhism confronts people with of who are you? What is this about? What are you as a person in this world? What is the meaning of all of this? Those existential questions, and it's not just Buddhism, of course, that confronts you with these things. I think, but I think there's a parallel in that the part of the Zen practice is to confront you a bit more forcefully, like not let's idly speculate about who are you, but like, who are you right now? Who are you? Answer the question. And you're like, I don't know who I am. What am I? I'm just this thing. The sort of bafflement it makes you very uneasy in a sense, but I think is also a sort of a gateway to like a deeper investigation of yourself. And in the same way, I hope that these questions that are in Cosmological Koans are kind of a gateway to deeper investigation of reality, of the physical universe that we live in.
Yeah. It wouldn't be the first time, though, that members of the Buddhist persuasion were practicing physics in your part of Northern California. As our mutual friend, David Kaiser, pointed out in How the Hippies Say Physics. Many of them were not located too far from where you are in our lovely city to the north. I do miss it, and I hope we can get together in person one of these days. Either you come here. I've been there a couple times, including around the Bicep 2 affair, which we just celebrated. It's March 2021. We're recording this now. We just celebrated the 7th anniversary of the announcement of Bicep 2's, ill-fated announcement. But you were kind enough to invite me to give a colloquium there. And I had a wonderful time, and I met some wonderful colleagues of yours. And in fact, I'm remembering you do quote Freeman Dyson actually in one of the chapters of the book in correspondence with Dick Feynman, with Richard Feynman.
Right.
Who I'm sure we'll get to. But in this concept of, what sounds crazy, maybe so, but it may be true. And I think, there are these interesting kind of koans. And so you've answered that because I think it kind of aligns itself nicely with what we do in physics. It is sort of, these inscrutable things that the more you think about it, the less you understand, perhaps. But maybe, as Wheeler said, you're just pushing that's a byproduct of this game. And I think, maybe just combining the Bicep 2 experience with this book and with what you talk about. I often thought during Bicep 2 that there, obviously there was a huge competition to win, one of these, which, one of my guests, John Mather, left.
Is that filled with chocolate? What is in there?
I can't say. But the competition to do that, I think, to win a Nobel Prize. And as I said, I have Michio Kaku coming on, and he's not afraid to be a little on the woo-woo side of things. But in his new book, The God Equation, he keeps tweeting out that, you can be the next Einstein and win a Nobel Prize and be a physics god if you can discover this equation, which is 1 inch long, and it contains all the mysteries of the universe. And first of all, what kind of font, could you write, even the laws of strength? But I want to ask you, one of the questions I've been really ruminating on a lot lately is, do we need a theory of everything? And this is kind of Brian's koan. Actually, I have a couple that I'm going to run by you for, the second edition of Cosmological Koans, which is just such a lovely book. I really feel like it's a book that you could give to somebody. I've been dealing with some extremely well-known individuals who are very wealthy, very successful, and they're like, I want to learn quantum mechanics. And I'm like, all right, well, let's start with trigonometry. And I'm like, if you put in the effort, you learn trigonometry, which is a prereq, you can learn it. But one of my koans is, is sort of, do we need a theory of everything? Like, who says there is a theory of everything? When I talk with Sir Roger Penrose on the show a couple months back, I said this to his face, or at least to the screen. I said, Roger, you and Hawking proved these singularity theorems and black hole theorems, et cetera. But the circular logic, which lends itself to the Keating koan, is to say, well, the only two areas that I ever hear we need quantum gravity for are for singularities in the black hole or in the beginning of time, if there was a beginning of time. And yet both of those are inscrutable, completely. We can't go through an event horizon. We can never get some data from inside of a black hole. We can never go back and observe the physical conditions at time equals 0, if indeed time had a 0 point, which you discuss in the book. So I want to ask you, what is it? What is it about? Is it just this need not only to wrestle with koans, but to come up with them ourselves? Because I don't see that there's some letter from God or from, the Buddha or from whoever, or from Feynman. I mean, just take Feynman as a God. He said, if it doesn't, I don't care how beautiful your theory is, Anthony, and you have some beautiful theories, but I don't care how beautiful it is. If it doesn't agree with the experiment, it's wrong. Now, I said that to John Preskill, who's the Feynman professor of physics at Caltech, and he said, I said, what about string theory? We can't even see if it's wrong. It might not even be wrong. And he said, well, you just have to try harder. So what do you say? Well, or is it a fool's errand? Is it a Buddhist quest? What is this quest for the theory of everything?
Yeah, there are a lot of pieces of that. I think one is why do we think of a theory of sort of fundamental particle interactions, including quantum mechanics and including gravity and including all the other fundamental forces? Why do we think of that as a theory of everything? It's sort of clearly not a theory of everything, in the sense that there are many, many questions for which that theory will be absolutely useless in predicting anything. So there's the very question includes a sort of worldview in which there's a sense of there are levels of description of reality. There's the everyday level with objects moving around and things and substances and stuff. There's a sort of chemistry level of reality. There's a particles and fields level. There might be a string or whatever level. So everybody sort of agrees that that is the case, that there are these different ways of looking at reality that are useful for different purposes. String theory will be totally useless for deciding, what the climate is going to look like next week. You don't need string theory. You don't want string theory. You can't use it. You want hydrodynamics and a climate model and a big simulation, right? So it's utterly obvious, then everybody agrees that these different levels of description of reality are good for different things. But there's also a worldview that says, but the lower down ones, the more fundamental ones, are more real and more true and more right in some way. And so as we get more fundamental theories, we are getting better and truer and more right theories until we get the most fundamental one, and that's the most true and most right, and that's the theory of everything. And I think, I never quite bought into that worldview. There always felt like something was a little wrong with that. But as a card-carrying theoretical, high-energy physicist, at some level I had to adhere to that creed for a long time. But I think, as time has gone on, I've just less and less been able to swallow that idea, that there's something more true or more right about the more particle or field-based descriptions of reality, and more sort of accepting of the point of view that reality is what it is. There are many different sets of tools that we can use to investigate and understand it, that reveal different truths and different things that are useful and not useful, and different ways of understanding reality using them. And they're consistent with each other to a large degree, that I won't find in my everyday physics of the world that energy conservation is totally violated and that things can just pop in and out of existence. And there are reasons for that I can sort of trace to what I call more fundamental levels of reality. But I can also trace things the other way, that given that the everyday world is the way it is, chemistry couldn't be that different. Particle physics couldn't be that different. These things are very connected. And what you call more fundamental, as I argue in one of these koans, is really rather unclear when you start to really analyze what do we mean by fundamental. So I, at some level, take a little bit of issue with the question of the theory of everything being a theory of fundamental particles or fields or strings or whatever. I think there may be some theory that we come to that we have trouble finding anything to improve upon, in the sense that we have trouble finding physical phenomena at that level of description that aren't accounted for by that theory. But that will not be a theory of everything, I don't believe. Now, in terms of the technical details of like why are we discontent with the theories that we have of quantum mechanics and gravity, as you said, there certainly are places where we know we can't just do with one or the other. That there are sort of physical paradoxes that occur, that if you just naively say something is gravitating like it is in general relativity and it's quantum mechanicating like it does in quantum mechanics, that you can't write down a consistent set of equations that make sense in both ways. And so that need is the need is there intellectually. I think I would agree that at the moment it's not there experimentally, in the sense that we don't have experiments for which you say, oh, I can't account for this experiment using the known physics that we have, other than questions about cosmology and like the nature of the dark matter, the nature of the dark energy, where relics like baryons that we're made of came from. So there are these cosmological questions, but as you know, it's very difficult to find things terrestrially that confronts us with some piece of experimental evidence that doesn't fit into the physical theories that we have. Mm-hmm. I think in that sense, we want those theories. We need them if we want to feel that at the sort of particle and field, very tiny microconstituent level of reality, that things are consistent and comprehensible. But I don't think that if we found a theory that did that, we could say, okay, we're done. We understand what reality is and how it works. And we don't, I'll get my T-shirt and we'll be done. We can pack up our bags and go home because, science is complete. That I say would be my feeling.
Mm-hmm. When I think about the book, can't avoid the impression that the setting of the book, and I always hated, Anthony, when you were asked to get on a podcast and the host says, can you tell us everything about this book? And maybe, so just save, $20 so that they don't have to buy an actual copy of it, please. I want to deliver value to my audience. We never ask for that. My audience gets the value from the guest and they read the book. Hopefully they will buy many copies of it. It certainly is one of the most delightful books I've read in a long time. It's really no parallel to it. Carlo Rovelli, kind of comes to mind, but even he had to submit that this is a gem of a book that he did not write himself. So I want to congratulate you on that. and I want to just ask you a question because I can, as the host of the Into the Impossible podcast, do this. I want to ask, why did you set it when you did? I don't think it will spoil anything to tell the readers that the book is a journey and it's an experience, but it kind of jumps between times. But it's always taking place in the 1600s. It interleaves the Middle East, the Far East, and actually Europe. And it takes place in some parts, before Galileo was Galileo, in a sense. And as you may know, Galileo is one of my heroes. I write about him a lot. I have even a figure puppet of him. Why did it
more of a fan than I?
Wait to see the one I have of you.
I don't have the puppets.
I have one of the Anthony Aguirre one over here. No, that's not one. Why does it take place in that time, and why does it take place where it takes place?
Yeah, so originally, so this is just a sort of a history of the ideas in the book at some level. Originally, when I thought about writing physics koans, I just started having ideas for ones that would take place in all kinds of different locations and settings and everything. So I just started writing them down. I then tried to kind of organize them into different time periods so I could have some sort of narrative. And I ended up with some that were taking place in Japan in sort of the 12th century. That's when the great Zen teacher Dogen was teaching. Some that were taking place in Italy with Galileo, and then some that were taking place now. But then it started to feel like there are three different time periods. Everything is not in order. Hard physics ideas. Nobody's ever going to possibly, even make it through this book. It's so confusing. That may still be true, but I tried to boil it down a little bit by picking one time period and turning it into a single journey. So the book does recount a single journey that, starts in Italy, ends up in Japan, takes 30 years or so of historical time. And although the koans don't happen in order, there is an order to them, which would be even fun to read sometime, the koans in the book in their historical order. Yeah. That would be rather different. So I think it's an amazing time because it is the birth of science, really, in the Western world. Well, the birth of science, period, at some level, with Galileo. I don't think that's any real exaggeration. It was astonishing. I'll fanboy a little bit on Galileo now. It was astonishing. You read his dialogues, and I basically transplanted one of them directly into Cosmological Koans, and attributed, of course, because they read so much like modern physics reasoning. I mean, you can just read them right now. They totally make sense. You're totally thinking, wow, he's really, oh my God. And that's true. If you go back and read Plato, Aristotle, for example, it's in a very different sense. You're confused reading it. It somehow doesn't connect. You have to really pore over it to try to understand what they're saying.
Yeah,
Galileo, it's like right there. It was like it was written last year.
And he even comes up with things that are, philosophical and psychological. I had this quote. I did a video called Deconstructing the Dialogue, and I actually read the whole book, which prompted me to realize, as I did with your book, I listened to it because I can set it on 2x speed and get through it in only 6 hours for your book. But Galileo, I was like, oh man, this book's 550 pages, longer than Anthony's book. This is going to be ridiculous. And I know people on my channel are getting sick of me always talking about this project, but I'm very excited about it because there is no audiobook of the dialogues, you may know. And reading it, it's one of the most delightful books, I think, in human history. There's a passage in this conversation between these three interlocutors where Sagredo, who's kind of the educated layperson, I'm going to play Sagredo in this work with Carlo Rovelli being Salviati, as you couldn't guess which role he's going to play. And then my good friend Lucio Piccirillo is going to be Simplicio, the simpleton. But the part that I get to read is one of them is the following, which goes by the name of the Dunning-Kruger effect in psychology, and it goes like this. Galileo writes, Sagredo says, this vain presumption of understanding everything can have no other basis than never understanding anything. For anyone who had experienced just once the perfect understanding of one single thing and had truly tasted how knowledge is accomplished would recognize that of the infinity of other truths, he understands nothing. And I think it's so cool because he's like basically saying, like, the more you know, the more you realize how little you know, but you also can have this false impression of your own abilities. So yeah, he is, and he's just an amazing writer. He talks about the value of money and what people trade for. He was kind of a stoic, and he had this kind of Zen quality to him too. He was, of course, not without his many foibles. But you're right. Going through this, so how did you choose 1608? Why not? I was thinking it would be me. In my book, I talk about him in 1610 after Siderius Nuncius is published. But why did you choose that particular period?
I should be, first of all, particularly clear that as a work of history, Cosmological Koans is, what's the polite word? Nonsense. It's based on, it includes historical figures, and I've tried to use real historical figures and a little bit of a sense of what was going on in these different places at this time. But it's also got a genie, and a vast conspiracy across the multiverse. So it's not to be taken as a historically true document. So I wanted to roughly, in terms of Galileo, pick a time where that would include the coming across the telescope. There's one koan that talks about thinking about telescopes and microscopes. I tried to make the experiments with falling objects roughly contemporaneous with when they were supposed to be. Mm-hmm. But I'm not a historian, and I'm not going to represent that anyone should read it as an accurate historical document. It's really sort of
fair enough.
To be read as
disclaimer noted. Disclaimer noted. Don't worry.
Yeah, the physics I tried very hard to make exactly right, but the history. Yeah, I will. If historians read it, I can only apologize.
So, but I found it, just completely delightful. But the Zen master that you mentioned, Anthony, that was a real figure. I'm just not familiar with that aspect of Zen Buddhism.
Well, Dogen didn't appear in this book because I put it all in the 17th century. So, so he was earlier. There's some quotes by him. The 17th century coincides with the kind of the period in Japan, the Edo period with the shoguns and samurai and all that sort of thing. Mm-hmm. So it was interesting there. There was a book on my my father's bookshelf, The Unfettered Mind. So The Unfettered Mind is a book by this sort of swordsman and Zen master that was sitting on my bookshelf as a kid, and I was fortunate enough to grow up in a house that had, I had a father who wasn't a physicist or a scientist, but he had a deep abiding kind of lay interest in it. So his bookshelf was chock full of Paul Davies and Michio Kaku and all kinds of entrancing books about how weird the world is. But it also included some Eastern books, and one that I remembered is The Unfettered Mind. So I was delighted to come across that this was exactly the time period where the author of that book lived. So it's always fascinating when you see, just like with Galileo, something, you pick it off your bookshelf and find that there was this living, breathing person back there that wrote these words and that are coming to you. It's kind of a magic thing, that you can reach across history like that and really make contact with someone. But he was at this time. And so I sort of picked interesting historical figures and tried to weave them into the narrative of that sort of archetypal journey from west to east. Also, I think there's that sense of I don't want to be demeaning to the West here. Obviously, it's also a journey sort of from youth to maturity as it goes on, because the protagonist sort of leaves Italy as a youth and arrives in Japan as a middle-aged person after having traveled the whole world. So hopefully they've accumulated a little bit of wisdom. So there's a little bit of that sense as well.
Yeah. So I want to talk a little bit now, as we move away from the book, about your research in cosmology. And actually, the last kind of stepping stone from the book will be, there's kind of a beautiful passage. You talk about inflation, you talk about the steady state theory, and many other kinds of kind of explorations of modern cosmology in the 20th century and what we know now. And there's a passage where you talk about inflation and the eternal kind of chaotic inflation of Linde and others. And you say that in a certain sense, we find in doing so that you get the Big Bang, kind of stitched into the steady state. In that you kind of make it. So can you expound upon that a little bit more? And then I'd love to talk to you about, you may not recognize this room, but this is the office once held by the late, great Jeffrey Burbidge.
Oh,
and Jeff inhabited this office and was not a big fan of the Big Bang, as you know.
Right.
And actually, you did some of the most recent work that was quoted in my book on ways you could salvage the Big Bang. You could salvage the steady state model of Jeffrey Burbidge. But can you first tell us, what do you mean by stitch the Big Bang into the steady state, or maybe even vice versa could work just as well?
Yeah. Well, yeah. So what was beautiful about the steady state theory just to backtrack a little bit, there were two kind of rival theories that were in the cosmological world in the 50s and 60s and a little bit the 70s. The Big Bang model, where the universe started in some hot, dense, early state a finite amount of time ago and has expanded since then, and the so-called steady state. And the steady state similarly had an expansion, but it had an additional property that the universe was and always will be more or less the same at all times. So the steady state, although the universe evolves locally, globally, it's kind of always the same. And what was really appealing and I thought beautiful about this theory is that the Big Bang theory is based on what Einstein called the cosmological principle, which is that there isn't a special place in the universe, that everywhere in the universe is kind of the same as everywhere else. There isn't a center, there isn't look, this is the top of the universe or anything like that. Everywhere is, statistically speaking, more or less the same. And if you go on a large scales, it looks more or less the same. And the steady state just extended this time. They said there's not just no special place or direction in the universe, but there's no special time in the universe. Every time is more or less the same. So it's a kind of more symmetric, more organized, in a sense, more principled version of the universe. Slight defect of this theory was that it was just wrong. Observationally, it does not appear to be a case. So there are things that are evolving that we can see. And, this was true in the 70s and 80s, but is super true now. There's just simply no way you can make a steady state like idea work for the observed universe. And so we kind of vacillated Big Bang, steady state, and Big Bang resoundingly triumphed in the sense that the observable universe appears to follow the Big Bang theory. But this really interesting thing happened, I think, which is that the theory of inflation, which was devised essentially as an explanation for the early conditions of the Big Bang theory. Why does the universe have these particular properties at this early time, that it is hot and more or less uniform and dense and expanding with just the right level of fluctuations in it? Why does it have those properties? The inflation was devised as a way to explain those properties based on some fairly simple set of physics and processes, and it does so quite beautifully. And so it was thought of as sort of this little fix that you would stick into the Big Bang. Like there was a messy kind of universe that was a Big Bang-ish. Stick in inflation, it fixes everything up, and the universe is nice and very Big Bang, uniform, isotropic, expanding, doing all the right things. Sometimes when you change just a little bit of something, you find that it has much bigger implications than you thought. And what has happened with inflation is that it was discovered fairly early on and developed ever since then, that inflation very much has a life of its own. The very properties that allow it to fix the Big Bang also give it these semi-magical properties of being able to bring into being a tremendous amount of space-time and matter to fill it. So the particular properties of the substance that has to drive inflation, the inflaton field, is that it essentially creates more space. It creates this anti-gravity force that blows the universe apart. But as it blows apart, it doesn't get any less dense. So you create more space, but also just the same amount of energy filling that space. And so it's this feels like cheating kind of process. There are ways in which it's not cheating that you can sort of talk about, but it feels like cheating. It creates this gigantic space, more or less out of this tiny little bit. But this process is very hard to stop. So once it gets started, it's very hard to stop the universe from inflating and blowing up and creating more and more space and time. And so what people discovered early on was that if the physics is right for it, and it often is, what you'll find is that it doesn't stop. It only stops locally in some little place, and that looks like a Big Bang universe like we see. But elsewhere, inflation just goes on and on forever, never ends. This is called eternal inflation. And once you admit that possibility, or once you sort of postulate a theory that has that property to it, then the large-scale picture of the universe becomes much more like the steady state, because this inflationary process that goes on forever, you can show that what that actually looks like is that the universe is more or less the same at all places and more or less the same at all times on very large scale. So it's a revival of the steady state. The eternal inflation is a steady state picture in which here and there little Big Bangs kind of go off where inflation stops and a Big Bang cosmology begins. And so I just find it fascinating that this vacillation between, Newton thought that the universe was infinite and, infinitely old, infinite age, infinite in size. Then we replaced it with the Big Bang, and then there was the steady state. And now we have this crazy combination of the two, where locally it looks like a Big Bang, but globally it could be this very big steady state picture. So it's an amazing thing where, again, you think you've got it all worked out. Oh, the Big Bang, it's right. The universe is 13.8 billion years old. We understand it all. But then you realize, well, okay, that might be just this tiny, tiny little speck in a vastly bigger and more complicated background.
That's very delightful to hear it from the man himself, who has, I believe, the honor of the actual description being attributed to you in the Encyclopedia Britannica. Is that not correct? That you have described the multiverse. Yes, the multiverse.
That sounds more impressive than it is. I think it's true that Encyclopedia Britannica when they had run through everyone else, landed on me to write the entry for Multiverse.
So it's like I used to get these things like, you have been selected to appear in Who's Who among, American individuals or something. And if you pay the $59.99.99, you can appear in the next edition.
So I was the sucker that said yes to the please write an article about the
Multiverse, a collection, hypothetical collection. So that's what I want to get into. Of potentially diverse observable universes, each of which would comprise everything that is experimentally accessible by a connected community of observers. And you go on a little bit. I want to ask you, when we hear about that and we hear about the string landscape, I am going to be having a conversation, quasi-debate with a intelligent designer who is an intelligent designer. His name is Stephen Meyer. He wrote a book called Darwin's Doubt and another one called The Signature in the Cell. And he's got a new book called Return of the God Hypothesis, in which he does battle with Lawrence Krauss and others over some of the necessary but perhaps insufficient descriptions of fine-tuning that there is in modern cosmology and modern molecular biology, et cetera, et cetera. But he also goes through the string landscape and talks a lot about that and necessary conditions for string theory to produce a multiverse-like entity. I want to ask you something that I've never gotten a great answer to. So we often hear, and you describe this in the book too, that it might be possible in such a multiverse to get any value you like of any of the physical constants, which in some sense might alleviate the so-called anthropic principle paradox, which is a type of Koan, I suppose. But in other cases, it might make it even more complex because the sheer number of universes that could exist according to string theory, 10 to the 500, 10 to the 1,000, and you go through this and you go through some of the objections that Penrose himself had with entropy when you describe entropy in the book. But I want to ask you a question. I often hear that we'll have different laws of physics in each one of the string landscape models, or maybe even in each of the multiverses. So I have two questions. One is, why is it that just changing the vacuum, the VEV, the vacuum expectation value, in a string theory Calabi-Yau manifold, how does that change the laws of physics? In other words, would there be 5, fundamental forces? Would there be 100? Would there be 1? That's question number one, and you could choose to answer it or not. And then question number 2 is, why stop there? In other words, why only the laws of physics? Why not the laws of mathematics? Why would anything be the same in any of these universes that are completely different entities from the one that we inhabit? So first, why does changing the vacuum value of the energy of a configuration called a Calabi-Yau, why does that lead to different laws of physics?
Yeah, so what's left out of that sentence is a few words. So what they really mean are, it will lead to a different set of low energy effective laws of particle physics. And this is very important because the assumption is that the two sort of pillars of physics, quantum mechanics and general relativity, as they might be combined into string theory in this picture, they're unchanged. So there's still this, in this sort of paradigm or kind of way of thinking, there's still this kind of Platonic idea that there are some fundamental laws of physics that are mathematical in form. They exist sort of transcending physical reality in some sense. They're the same everywhere and at all times and everything. And those are, string theory, which includes quantum mechanics, string theory, which is sort of based on quantum mechanics and includes general relativity, but then also includes these other sort of local lesser forces like electromagnetism. So that's an important distinction, that some of the laws of physics are held to be the same everywhere and at all times and in this sort of transcendent sense. And other ones are thought of as kind of local conditions, much like the laws of hydrodynamics sort of work. Well, there's some particular, rules of hydrodynamics that function in this room that are particular to the setting of this room, and elsewhere, the laws might be similar, but there'd be different conditions. There might be more different gases involved. There might be, some different some different boundary conditions of a window open or whatever. They're more local things. So the excuse me. So the way that story works is that, as you said, there's this string theory, and there are these. This is a bit of a long story, but to make it very short, it was shown, actually not that long after Einstein's general relativity, that if you had extra spatial dimensions, the behavior of fields in those extra spatial dimensions, when you confine yourself to less dimensions, so if you had a 5-dimensional space, or space-time rather, 4 dimensions of space and 1 of time, if you confine yourself to 3 dimensions, for one reason or the other, like the extra dimension is really small, or you can't get to it, or for some reason you can't access that other dimension, so you just get to experience physics in the 3 spatial dimensions that we have, that there will still be a sort of manifestation of that extra dimension as fields that are in our space that have properties and dynamics. So what they showed in particular was that if you had 5-dimensional space-time and general relativity, you could get from that 4-dimensional general relativity 3 spatial, 1 time dimension, plus electromagnetism. It just kind of came for free, where the field, that the electromagnetic field essentially is another name for this extra hidden dimension, in a sense. This was by Kaluza and Klein. And the idea of string theory is that it's this on steroids, that all of the stuff that we call electromagnetism and the strong and weak force and the symmetries that they enjoy are all really properties of these hidden extra dimensions. And so if you change the properties of those hidden dimensions, which can physically happen in different places and different times, then you change the properties of the effective physics that you see in our pedestrian, small, 3+1 dimensional universe. And so we say, oh, look, there's 2 versions of electromagnetism, or there's no electromagnetism, or there's an extra strong force that behaves differently, or whatever. They emerge from those extra dimensions in just the same way that electromagnetism does in the Kaluza-Klein theory, and there's no reason that those can't vary from place to place. While at the same time, general relativity, again, and quantum mechanics are the same everywhere in this picture.
So then that would explain why the laws of mathematics wouldn't change, or laws of logic, or could you envision multiverses where even, 2 + 2 = 5?
I think that's a fairly different question. I think you can, it's certainly the case that the sort of multiverses that, there are many different versions of the multiverse, right? There's the one that I just described, the string theory inflationary one. There's the quantum mechanics one, for believers in the many worlds version of quantum mechanics. And in that one, all the laws of physics are essentially the same, and it's just different branches of this wave function. Then people have entertained sort of more even diverse multiverses in which the question that I believe Stephen Hawking asked, there's a particular set of laws of physics. Why does reality breathe life into this set of laws of physics and make a physical world that is governed by them, but not these other ones? That's an interesting question. And one answer to that question is that, that's not what happened, that all of the sets of equations have life breathed into them, and they all exist in the same way that ours does. So that's a point of view that, Max Tegmark and some others have taken, that every set of physical laws that exists, with presumably every set of boundary conditions that there could be, correspond to a real physical universe in just the same way that, the ones that we seem to experience do. And I think that's an interesting and sort of self-consistent answer to the question of why one particular set of laws of physics are the laws of physics, are real, get to govern a universe. Why are they so lucky? And all these other sets of laws of physics don't get to govern anything. So I think that, that's an interesting idea that's very hard. It's not one that I personally believe, but again, belief is it's not. It's one of the things that if someone says that's crazy, I will defend how it's not crazy. If someone says that's true, I will defend how that's totally crazy. So it's one of those things that I think the right response to it is, yeah, that's crazy, but it could be true. I don't know. And there are a lot of those things.
It's funny because I have a guest coming on in a couple of weeks who has caused me to reevaluate my views of Stephen Hawking. He wrote a book called Hawking. It's a critical biography of Stephen Hawking. And actually, I had finished reading A Brief History of Time. I started reading it in 1989. I finished reading it in 2021. And it wasn't only because it was some parts of it are a little bit dense, but actually that was the obstacle in the beginning. And then by the time I was done with it, and I was a full professor at UC San Diego, I fully understood it, and it was parts trivial. But there are parts within it where he talks about work that he did with our other colleague in the middle of the state, Jim Hartle, about the Hawking-Hartle no boundary proposal. And I started to realize he was an excellent writer. Actually, the book has almost no complaints from me about it, because I really love his writing and his character and the things that he says. But and upon reading it as a mature person, I found it very suspicious, the things that he did, especially even in the revised third edition, I think is the one I read from 2016. So this is after Bicep 2. This is after, many things. And he really made the case in that book. There were two, real purposes for a God in a universe. And one was to create originate the universe. What role for a creator if time didn't have a beginning? And that was the notion of the no boundary proposal, which is the basis of A Brief History of Time, which I only realized as a fully tenured professor. And then the other purpose for God would be to instantiate the laws of nature, and he claims that was provided in the grand design by M theory. And I started thinking about this, like, neither one of those has, any observational support, at least right now. It's very troubling to think that, he really, in one hand, in the no boundary proposals, he basically says, well, if you make time imaginary, do what we physicists call make a Wick rotation, you can transform away all the time-like properties of time and make it a spatial dimension that will be like a dimension on a sphere. It has no boundary. It may be compactified, but it has no boundary. And he even says in it, this is just a mathematical trick. And later it's like, now you see, we don't need a beginning of time, so what need for a creator? And if we can get the laws of nature, we'll know the mind of God. I mean, that was one of the first times he said that. Yeah. And I just found it a little disingenuous that he would do such a thing when he knew for sure that it really wasn't so solidified. Even Hawking-Hartle, I don't know how many people really put faith in that no boundary proposal, other than an interesting way to solve the Wheeler-DeWitt equation, perhaps. But I want to get into, because you gave an incredibly popular talk at the SETI Institute about bubble universes and all. Has your thought process evolved, since your earlier days when you made really fundamental contributions to not only our understanding, but kind of popularizing these bubble universes that go on for without end? I really think of you when I think about that. Have you evolved in any way? I mean, has Bicep affected you as, other branches of physics, or are you as sanguine as ever, so to speak?
Well, I think if you're asking about how have I evolved in terms of like how probable I think it is that inflation is true, or that eternal inflation is true, or something like that, I would say fairly similar to how I've always felt. That inflation seems like a good and relatively unrivaled explanation for how the Big Bang has the properties that it does. And eternal inflation seems to me like a, if not inevitable, quite natural thing to happen with inflation. And so I think both of those are, to me, just as likely as they ever were. It certainly would have been nice to see evidence of, colliding bubble universes in the microwave background and prove that was happening, or at least get evidence for it. But even when I was thinking about those questions, I figured that was very low probability that we would be so lucky to see those. So I think it's been frustrating in the sense that some things that could have happened that would have made things a lot more interesting and exciting haven't. We haven't discovered gravitational waves from inflation. We haven't discovered supersymmetry or anything else of interest in colliders. We haven't discovered colliding bubble universes or other defects. We haven't discovered anything wrong, with the standard model of cosmology and the microwave background radiation that we can really point to, which is super frustrating.
Yeah.
But all of those things were at least a little bit hopeful. Some of them were more hopeful than others. There was certainly a higher probability we were going to see gravitational waves than colliding bubble universes. But there are plenty of versions, as you know, of inflation where you don't see gravitational waves, right? Mm-hmm. And so we've been unlucky, I would say, relative to how, we could have been luckier, but there hasn't been anything in the sort of progression of the experiments that have led me to say, well, we've got something terribly wrong, or like we're misguided in this whole picture. Just that, frustratingly, it's a bit harder and going to take longer than we had hoped to pin some of these things down. I would say, though, that my excitement about figuring certain things out has shifted a little bit. So when I was first studying physics, in college, if I had been able to skip the thermodynamics course, I would have enjoyed that, or statistical mechanics. It seemed like the most boring subject. Like, yeah, there are lots of particles instead of a few. So what? And it just seemed like a mishmash of different ideas, and it kind of was useful for some things, I could admit that, but it didn't seem really that exciting intellectually. And that's something I've really changed in. So I've spent the last 5 years or so really thinking about statistical mechanics and its foundations and these questions. And this goes a little bit farther back about the arrow of time and cosmological boundary conditions, all of which are wrapped up in this big, interesting, and information theory, all of which are connected with each other and have become much, much more fascinating to me. And so I think my interests have changed, and what I find personally compelling as questions to investigate has changed. But I don't think my beliefs about things like inflation or the multiverse have changed that much. Now, in terms of...
Yeah, go ahead. Sorry. No, keep going.
In terms of Hawking, I think I've always been very frustrated with this idea that, creating the universe from nothing in the way that they talk about it with the Hartle-Hawking, or Vilenkin with this tunneling wave function, or any of the other versions of kind of creating the universe from nothing. I've always felt, and I think they admit this if you press them on it, that it's totally cheating, right? That the nothing is a very particular meaning of nothing. But it includes the laws of physics and, a Hamiltonian
Hilbert spaces and
Hilbert space, like all the mathematics. It's all there. It's a particular nothing, which is like a universe of zero size. You sort of look at the universe in the zero size limit and you call that nothing, but it's really not at all nothing. Right. So I think it's important to the question of kind of why there is something rather than nothing is just, those studies address it a little bit in the cosmological context, but they really leave the meat of that question very much untouched, I would say.
Yeah, it is sort of unsatisfying, but then again, koans are not meant to necessarily be delicious repasts. So in the final, few minutes that we have, you have another 10 minutes, Anthony, or
yeah,
you have a pretty hard out, but I can't resist. This is so delightful for me. I want to ask you a simple question. What causes time? No, I'm just kidding. That is a koan in itself. I want to bring us back to some of your papers that you did in the late 90s. Actually, they were just solo papers that you wrote, and some of them appear in my book, and they involve kind of what it would take to
Dust, your favorite subject.
That's right. Yes, the villain of my book, the djinn of my book, is sort of dust. And, but when I think about those papers, you were kind of doing something radical, which is to, perhaps try to reconcile the standard lore is that after Penzias and Wilson, the Big Bang won and quasi-steady state was over, and of course nothing could be further from the truth. And in fact, the inhabitant of my office, the former inhabitant Jeff Burbage, went to his grave believing that the Big Bang was false and total rubbish. Worse than that, or better than that, I spoke to Jayant Narlikar on the podcast 2 or 3 months ago, along with his wife, who's an eminent mathematician, and we had a wonderful time. And he still publishes books, fundamental problems in cosmology. It's sort of, I think it comes down to an uncomfortability, a discomfort rather, with singularities, with beginnings of time. It's not at all clear that the Big Bang solution was really as dispositive as most people think. And I pointed out in my book, the words Big Bang don't appear in the companion paper to Penzias and Wilson. It was they only discussed that was by Dickey, Bob Dickey and Peebles and Roll and Wilkinson. And I have on my advisor, who was one of your former teachers, Peter Timby, he was a guest on the podcast that's in an episode that's coming out soon. But anyway, we talked about Dickey and what he really felt about the Big Bang and that paper. And again, it mentions a cyclic universe. It doesn't mention the Big Bang at all. And it's not like they didn't know about it. So when people say, these guys are fools, Hoyle and Burbage and Narlikar, I don't, I'm much more sympathetic to them. And I kind of see these echoes going on, right now with my friend Paul Steinhardt, Neil Turok, and others, who are maintaining kind of versions of cyclic or bouncing cosmologies. And they're often ridiculed or, as outsiders. And don't they know how successful inflation is? But I think you point out a lot of these things, the fine-tuning problems, the entropy problems. What would you say? I asked Sean Carroll, over lunch once when I was interviewing him a long time ago. I said, what are the odds that God exists? He said, less than 0.5%. I said, okay. What are the odds that the multiverse exists? And he said, 50-50. So, you just said, you're disappointed, or it is disappointing we haven't collided with another universe. I mean, the odds of that are pretty low. And I want you to be happy and not depressed if this doesn't happen in the future. So, when we think about this, how much of it is wrapped up in our need to want to believe a particular type of story, kind of sociology, which you do get into in the book. Like, how much of physics is really sociology?
Well, I'm not sure. There's two separate questions, I think, there. One is, why there's a question of why, a small minority of physicists continue to believe something when it seems so difficult to believe at this point. And I think there's a fascinating recurring theme where I would say there's a sort of mainstream that believes a version of physics or of cosmology a little bit more strongly than they ought to, given the evidence. Mm-hmm. And then there's another set of people who say, you're believing that a little more strongly than you ought to, given the evidence. What about this possibility? Okay, and then there's a vicious fight where everybody circles the wagons and identifies themselves with this belief, which is always a tricky thing to do. But the nice thing about science is that as you progress, one of those things actually does turn out to be right and true, and sort of evidence keeps accumulating for it. And that community of people who are doubting it shrinks and shrinks. But I think it's great that they don't entirely go away, because it's always useful to have people who are sort of playing the gadfly and pointing out that the evidence for things is not quite so secure as you think it is. And so I think that happened with the Big Bang and the steady state. And what I studied in the late 90s as a grad student, the cold Big Bang model. Yeah. So when I came across that, I figured this is not likely to be true, right? It's probably true that all these people with the hot Big Bang model are right, but they're kind of a little bit overconfident given what the evidence actually is. Let me see how hard is it to make this cold Big Bang model work? Like, what really would it take? Is it so crazy? What does the evidence look like? And I think putting that was a great exercise for me to understand both how hard it is to develop a whole cosmology and have it all fit together, but also how strong the evidence was in some places and how not so strong it was in other places. So once you get off the bandwagon and look at a theory from the outside, you I think discover, those pieces of it really are very secure, and well, these are a little bit more iffy. So I think it's very useful to have people around who will play that role and who will take that outside perspective and point out where the weaknesses actually are. But I also think that, as a practicing physicist, there's a point where things just get boring. So the cold Big Bang model got boring for me, after spending a while on it, because it just wasn't fun anymore to try to massage things into making sense when they didn't quite fit with the data. Mm-hmm. The same thing I think happened with modified gravity. There was a nice idea that maybe, in the 80s, that maybe what we call dark matter is just a change in gravity at very low accelerations or large distances or something. Not a crazy idea at all. Mm-hmm. When Einstein's, the first manifestation of general relativity showed up as this precession of the perihelion of Mercury, and people started to invent different, clouds and asteroid belts and stuff that would account for that. They call dark matter, but it was a modification of gravity. Not a crazy idea that what we call dark matter is a modification of gravity. And it was an interesting idea in the 80s and a little bit in the 90s, and it just got steadily less and less interesting as more and more data from all sorts of directions just was perfectly beautifully consistent with dark matter and not with modified gravity. So yes, you can still concoct very complicated, multi-component, arcane versions of gravity that could sort of explain dark matter and some phenomena, but it's just not fun anymore, right? Mm-hmm. And I think there's, it's not so much, there's this saying that, you have to wait for the old generation to die off,
right. to physics progresses one funeral at a time.
Exactly. I don't think it's quite like that. I think it's, people get bored with thinking about things that don't seem to be true. And then there's a few holdouts, and it might take a funeral for them. But I think in all, it's a fairly healthy thing. And I think, honestly, something similar is happening in string theory. I think people are streaming out of the field at some level because it may be true, but it's gotten a little boring to keep coming up with these beautiful theories and mathematics and working things out, but not having the feedback process that gives you more clues as to what's going on. And so the string theory community is branching off into lots of fun, interesting directions in terms of thinking about the black holes and information theory and condensed matter physics and all these different things. But the idea of just let's figure out a theory that gives us the electron mass from fundamental considerations, people have tried it and it's not that it's exactly failed, it's that it kind of isn't that fun anymore to do. Mm-hmm. So that I think it's not the case. I think it's the case that I can't remember exactly how you posed your question. How much physics is sociology? I think there certainly is a lot of sociology in the practice of physics and, creation of these communities and bickering with each other and things that are fashionable for a while and more fashionable than they ought to be. But it's also really gratifying, I think, that in the sweep of time, the physics community, like other scientific communities, do seem to converge on things that they agree more and more on and seem to be more and more true. They really do explain better. They really do work better. You come up with new phenomena and they still fit that new theory, not the old one. So the whole process, I think, is a really beautiful thing that we've devised. Going back to Galileo, he couldn't have known, probably, how amazing a thing it was that he invented this consensus truth-finding practice that has led us over these 400 years to the place that we are. It really does work, and it's an amazing thing. And there are lots of criticisms you can make of science and lots of ways that it goes wrong, but I think we have to keep in mind what an extraordinary enterprise it is.
Yeah, and of course, Galileo was not without his faults. He believed until his dying day that certain things about the universe were completely different than the way that we know them are to be now. I mean, I don't know if you know what the original title of this book was, Anthony. This is kind of a test to see if you've subscribed to the podcast yet. I hope you will. So this is the dialogue, of course. So the original title, just to save you the trouble, was On the Flux and Reflux of Tides in the Earth's Rivers, Oceans, and Ferns. I don't know if you have any ferns up there, but we don't have any ferns over here. But the point being that he thought that the most dispositive piece of evidence for the Copernican universe was the sloshing of water, that was caused by the combined motion of revolution and rotation. Of course, we know that's completely wrong.
Wow.
He also believed that the comets were in the Earth's atmosphere, but certainly that notion of confirmation bias. Now, look, he was right. The Earth, does go around the sun. But that was completely wrong information for it. Anyway, I hear some buzzing. I got to go. I know you got to go. Do you have like 2 more minutes, or should we wrap it up?
I'll give you 2 more, and then I'll feel very guilty to the prospective grad students who are probably waiting for me in another.
Maybe that's my ploy to get them to come here. Okay, I want to ask you. Actually, I'll just ask you. Two questions. One is, what would you put in your ethical will? An ethical will is a wisdom will. It's a type of a piece of wisdom that you want to bequeath to your ideological heirs, not necessarily monetary to your biological heirs. What would you like to give most?
Let's see. Yeah, I that's a difficult question. I would say that I would probably want to impart upon the younger set of them, perhaps, that the questions really are the fun part, not the answers.
Awesome. That's beautiful. The last question I ask all my guests is kind of a version of Feynman's cataclysm question, except in this case, since I'm the co-director of the Arthur C. Clarke Center for Human Imagination, I used the monolith in 2001, A Space Odyssey, some time capsule that lasts for 1 billion years. And so Feynman was asked once, what would you put that encapsulates all of scientific knowledge if civilization were to be destroyed, that contains the most information and the fewest words, kind of a koan of his own? And he said it was the atomic hypothesis. What would you put in? What discovery have you made in your really eminent career? I'm so, I can't be proud of you, but I'm so impressed by you. You're kind of like this old guard of physics that's somehow fallen into this my generation. But I want to ask you, what would you put that encapsulates the wonder of knowledge of science that you've discovered by yourself, or the combined talent of all the scientists in history that have led to this point?
Boy, you have hard questions.
Speaking as a koan asker, come on.
I would. I think I would say, and this is not so much a summary of the way physics is now, but I think more of an injunction of the way it is in certain ways and the way it ought to be. I think physics is to a surprising degree constituted to make the world safe for observers and about observers. And that sounds totally contradictory and against what you would think about physics. But I think to think about the universe is both objective and constituted so that it makes sense and has a consistent story to every observer in it. When you manage to reconcile those, you have something of interest.
Well, that has officially blown my mind, my brain, and makes me want to get you one of these dolls now. This is a Carl Sagan doll.
Is that a Carl Sagan? Where do you get these things? Do you make them?
No, I have a team of graduate students no, it's a place called the Unemployed Philosophers Guild. You can get them yourself. But you deserve one. But you echoed something earlier where you said, it's amazing to read something. And Carl Sagan said, books are proof that humans can work magic, because over the centuries, a long dead writer can be speaking to you. I like to say a podcast is proof that humans can work magic, because we can see you, we can hear from you, and we can learn from you. And Anthony, I want to wish you all the best up the road in northern part of California. We love what you do. We hope you'll come back. We didn't get to talk about FQXI. We didn't get to talk about future of life, all that fun stuff. Go attract some graduate students to become banana slugs. We love you, and wish you a wonderful rest of your quarter, etc.
Thanks very much. It was just a tremendous pleasure to be here, and thanks so much for doing the service that you're doing and making this show to bring all of this fun to lots of people.
It's my pleasure. Bye, Anthony. Be well.
Any sufficiently advanced technology is indistinguishable from magic.